Today we're going to reuse what we saw last week, those basic elements, but now we're going to focus on some practical libraries for dealing with data. First, in the morning, I'm going to start with the Numerical Python library, NumPy, which is useful if you have to deal with tables of numbers. So if you have to operate with vectors and matrices and things like that. And also, we're going to take a look at SciPy, which is useful for computation. There are a lot of things you can do with SciPy, but I'm going to show some examples of fitting a model to data. So basically, if your work is focused on numerical data, you don't have to deal with things like names and addresses and text, things like that. This should be the most useful library for you. You can do mostly anything with this one. In the afternoon, I'm going to cover Pandas, Python for data analysis, another library that is useful when you deal with tables with heterogeneous data, with text and numbers and categories, things like that. So this is a package. It has modules for algebra, for doing operations over arrays of numbers, multidimensional arrays, and it's basically it offers objects that help you do computations with sets of numbers in any dimension. The most useful object usually is this NumPy array, which you can create using the array function from a list which can be multidimensional. You can have a list of lists, for example, for creating a 2D matrix of numbers. Now remember from last week, everything in Python is an object, so it has data and it has functions, methods that you can use to operate on the data. For example, you can create an empty list and then use append to add elements to the list, or you can create an empty dictionary and then insert new elements there, and so on. This NumPy array has also methods that are useful, and also it overloads operators such as product, sum, and so forth. So you can store numbers in the array and then do operations over all those numbers. For example, we can convert this list 1, 2, 3, 4 into a NumPy array. Now this is a different object. It's not a list. It's one of these NumPy arrays. And you can do operations with this object. For example, multiplying these numbers by the object, and the object knows how to do this. It will, if it has the same number of elements on both sides, it knows that it will do the multiplication for this with this array. For example, it multiplies this one by this two by this three by the four, and so forth. So if it has the same numbers, it can distribute the operation over all the elements. If it has only one element on one side, it can distribute between that element and all the others. So if we multiply this array here, which I stored in A, by 3, it will multiply each of its elements by 3. You can also do comparisons for all the elements. For example, if I ask if A is less than 3, it will do the comparison element by element and return a NumPy array with Boolean values for all the comparisons. So basically, these objects allow you to vectorize all these operations. That is, you apply them to all the elements in these arrays at once. It's also very efficient because this is implemented at a low level. It's much faster than if you do a for loop and do this one by one. These are examples of division, integer division and floating point division. So remember those two dashes. It means that we want the integer result from the operation and not the floating point representation. You can have different types of numbers stored there. For example, this array was created with integers, so it's an integer array. The type of data that is there. if you divide by 2 using this, the usual division, the result will be a floating point that is one representation that can handle the decimal point, the fraction. You can also typecast the array. For example, this array A is made of integers, but we can ask for the array as a floating point representation. So it will give us a copy of that array with a new, with the values in a different representation. So there's a lot of detail about NumPy. You can look at the documentation if you need to know more detail about this. But perhaps the most used feature is the ability to broadcast an operation between 2 arrays. And the rule for this is that NumPy, the object will compare the dimensions starting from the last one. And either they must have, the arrays must have the same length in that dimension, or there can be only one element in one of the arrays. So if there is one element, for example 3, it will broadcast the operation through all the other elements of the other array. If they have the same number of elements, it will do that element by element going along the array. So let's see a few examples here. This is how you can create a 2-dimensional matrix. You create a list of lists where each of the inner lists is a row on the matrix. So when you convert this into a NumPy array, this is a matrix with 2 rows. In this case, it will be a matrix of 2 columns. Each row has 2 elements and has 4 rows here. So this will be another matrix. You can do this in n dimensions, and usually you will not do this with like this way, writing in the values in the code. You probably will read it from a file or something like that. But the idea is the same. If you read from a file, each line of the file, for example, as a list of values, then you can put those lists in a larger list with all the rows, like we did before with the numbers we used last week, and then you can convert this into the array. Now you can index parts of the array in a way that is similar to what we did with lists, only it's extended to the number of dimensions that the array has. So this is similar to MATLAB, if some of you have used MATLAB. For example, here I can say that I want from this matrix 1, I want the second row and all the columns. So this one here, the rows are indexed at 0. Indexing always starts at 0. So the second row is index 1. And this column here means that I want all the values in that dimension. So this will give me this row here, the second row, and all the columns. I can ask for all the rows in the first column, and then I get these 2 values here. So, sorry, the second column, and I get these values here. You notice that when I ask for a single row or a single column, I get, as a result, a 1-dimensional array. So this is no longer a matrix of 2 dimensions, it's just a vector, it has 1 dimension. So it's neither a row nor a column, it's unidimensional.
When you ask for a column, you get a row?
No, you don't get a row, you get a 1-dimensional vector.
Yeah, but this one, array is 6,
you have a row or a column if you have a 2-dimensional matrix. Okay, so for example, this is a column. You see, this is a 2-dimensional matrix, and you have a column. This is a 1-dimensional vector. It has it's not horizontal or vertical because it just has 1 dimension. Okay, so in MATLAB it's a row, a 1-dimensional it's a row because MATLAB uses as a basic element, a basic type, the 2-dimensional matrix. So a 1-dimensional vector counts as a row in a 2-dimensional matrix. Okay? But that is something strange about MATLAB. So a 1-dimensional vector is not a row or a column. You cannot, for example, transpose it like you can do in MATLAB. Okay? Because it's 1-dimensional, there is no other dimension to transpose it to. But we can, if we want to preserve the same geometry, or the same topology of the original matrix, we can indicate the columns or the rows that we want as a list, even if it has only one element. So if we indicate that we want the second column, but as a column, so as part of this list, it will preserve the same number of dimensions in the original matrix, and it will give us, in this case, a column, a vertical column on a two-dimensional matrix. We can use this large T, or the transpose function, for transposing a matrix. Okay. We can use this for transposing a matrix, but this of course only works if we have more than one dimension. If you have a one-dimensional vector, the transpose will just be the same thing, it will not change anything. If you have more than two dimensions, you can want to specify the axis in which it will be transposed. So this large T is good for the general two-dimensional matrix, because in that case transposing always means the same thing. But if you have more than two dimensions, you can use the transpose method, where you can add arguments to tell how the matrix will be transposed. You can also do operations between the matrices, or between higher dimensional arrays, but remember the broadcasting rule. So the length of the array will be compared starting from the last dimension of each one. So you cannot multiply this matrix 1 by matrix 2 in this case, because the last dimension of matrix 2 is 2, it has 2 columns, and the last dimension of matrix 1 is 4, so they cannot be matched. But if you transpose, for example, if you transpose matrix 2, then this one will have 4 columns, the transpose of this one, and now you can do this operation, for example, multiply matrix 1 by the transpose of matrix 2, and the operation will be done element by element. This is the result. You can also do operations between matrices, or between arrays with different numbers of dimensions. And the broadcast rule applies here. So the last dimension of this list here, of this array, has a length of 4, because this is a one-dimensional array. That's a list. And this matrix has 4 columns. So what the object will do for broadcasting this operation is to apply this operation element by element to each row, where it can match each element of this array with each element of the row, because they have 4 elements, both of them. But then it will repeat the same thing for all the rows. So you can easily apply some operation with a vector of values that applies differently to each element of each row on a matrix, but then apply the same thing to all the rows of the matrix. This can be useful if you want to, for example, standardize your data, or normalize the data, or something like that, rescale the data. You can easily apply this operation. So this takes a bit of practice. Don't try to memorize all the rules, but remember 2 easy tricks. When you want to do something with broadcasting in NumPy, you can also always use Google and look up examples, or you can experiment. So the worst thing that can happen is that you get an error because you could not match the dimensions, and then you figure out why they are not matching, and either solve the problem by transposing the matrix or something like that, until you get it right. But the basic idea is always the objects will start by comparing the length of the arrays in the last dimension of each array, and then going back until one of them has no more dimensions, and that will be broadcast for all the remaining directions, all the remaining dimensions in the larger array. We can also index elements in a NumPy array using a Boolean array. The requirement is just that the Boolean array has the same number of elements as whatever we want to index. For example, if we want to index the rows of this array with a Boolean mask with true or false, we need to have an array of Boolean values with 4 elements, because there are 4 rows in this matrix. Okay? So as long as the array has the right size, you can use that to index the elements on any NumPy array. And you can easily obtain an array of the right size by doing these comparisons that are also broadcast. So if we start with this array, and we compare this NumPy array with 4, so this array greater than 4, we get an array of Boolean values that correspond to the comparison of each element of the NumPy array with 4. So all of these are false, and then starting from 5 onwards, it's true. And we can get the same thing, for example, another comparison less than 8. Now you can combine these Boolean arrays with logical operations such as disjunction, conjunction, and so on. You have these methods in NumPy, logical AND, logical OR, logical NOT, that you can use to combine these Boolean values. And you can use that to create masks for selecting specific elements in the array. So in this case, we can select from the array all the elements that are greater than 4, and we get this result, all the elements that are less than 8, or all the elements that are both greater than 4 and lesser than 8. So we can use the logical AND to combine the two Boolean arrays, and then index our original array with that Boolean mask. So these are the sort of operations that are very common when you're dealing with data, when you're extracting the points that you want, and NumPy makes it very easy to do this and very efficiently with your data. So let's see an example. We're going to use data from temperature averages for each year. We can get this data from the World Bank site. It has a programming interface that you can use to download the data for different countries. Basically, it's a very simple interface. You have a base URL here, and then you have the three-letter ISO code for the country, .csv, and this gives you a file with the year in the first column and the temperature, the average temperature for that country in the second column. So we're going to, I'm going to show how we can retrieve this data from the site, and then we're going to do some operations with the data, averaging, fitting the different countries, and so forth. Now, there's nothing here that is supposed to make sense from a climatology approach. I don't know anything about this, so this is just a toy example to show you how to manipulate data and how to fit models to the data using this data. So it's not about how we're going to actually process this data. So we can use one simple library. This URL lib is a simple library that you have installed that you can use to access data on the internet. So we're going to, from the request module, import this function, URL open. This is the one that allows us to download data from a URL. And I'm going to create here the global variable that I'm going to use as a constant for storing this long URL, which is the base URL here, the part that comes before the ISO code of the country, and it's always the same for all the countries. So this is useful to do it this way. There are two things here. One is this convention of using all caps for this variable name. In Python, you can always change the value of any variable that you use, so there is no notion of a constant, but there is this convention that when you write everything in all caps, then this is not supposed to change during program execution. So there will be nothing in my program that changes the value that is stored there. The usefulness for this is that this may eventually change. So suppose the API for this data changes to a new server or something like that, and to solve that we can easily change the value here on this declaration for this variable, and then all the rest of the program that uses this value will be updated. It's much better to do it this way than to repeat the same thing all over your code, because then it's harder to maintain your code. So remember those namespace rules that Python uses. If you declare a variable on your module, then any function can also look at that variable as long as there is not another one with the same name declared here. So since there is no base URL declared inside this function, when the interpreter reaches this point, it cannot find the name in the namespace of the function. It will look above in the namespace of the module and retrieves that value. So this way you can store these constant values that will seldom change in a practical manner, that if they eventually do change, you can easily update your code. Also, I use this here. Remember this slash, the backslash in at the end of a Python line tells the interpreter to consider the following line as part of the same one. So you can, instead of writing a very long line here, you can break it in different parts. So I use one string, then I concatenate it with another string and put this one in the second line. I only need to do this because I have limited space in the slide, but if you want to just put a single URL in a long line, there is no problem in doing that. So this is the function to retrieve data from the site. It receives as an argument the code for the country. This is the only thing that varies. And then the way we do this, we use URL open, is similar to how you use open to read files. You just call the function, tell, in this case, instead of the name of the file, you give it the location, the remote location, the URL for the data you want to retrieve. And this function returns an object that works in a similar way as a file object. So you can use the read method to get the data from there, or you can send this object to other functions that could also read data from files. And this is the case of this function, gen from txt, that NumPy has, that generates a matrix, a NumPy array, from a text file. So if you just give the same object to that function, the same object that you got from URL open, this function will now read the data from the remote location that you want, that you provided in the URL. There are some arguments that you may need to use here. By default, gen from txt will assume that the separator is a blank space, like a space, a tab, or something like that. If it's not, you need to specify the delimiter here, which is the character that separates the values in each row. And also you have this option, skip header, because sometimes you have numerical data in a file that also has non-numerical values. For example, some header with a description of the data, or the column headers, or something like that. So this skip header argument allows you to specify how many lines you're going to skip in the beginning before the data starts. If you don't do this and you have data like this, you'll get an error when the object tries to convert the year and date, in this case, into numbers, because it cannot convert those. So what this does is it returns this temperature data. What we store in the temperature data variable will be a numerical array of 2 dimensions with 2 columns, the first column being the year and the second column the temperature. So this is how we can get data from the remote server where the data is stored. We can also write an alternative function, because sometimes when you're dealing with remote data, it may be useful to download the data in one go and then use it from your hard drive. So if it's not too much data, if you can store it locally, that tends to be better, because it takes some time to retrieve the data, and if you have to run your code several times to debug, to test things, then it's best to use data that you have stored locally. So we can also write a different function that is very similar to that one, but to read the file from our local hard drive instead of from the remote location. We're going to assume that the file has the name for the file is the 3-letter code for the country, .csv. And we can also, this is also to illustrate another application of gen from txt. You can use this function instead of giving a file-like object that can be the result of opening the object or of this URL open. You can also give a string as the first argument with the name of a file. In that case, this function will get the data from that file. So we just create a file name that we assume to be the ISO code of the country.csv, and we use the same function to read the file from there. So you have two examples here of getting numerical data either from a remote server or a local file and immediately transform that into a NumPy array that we can use. Now we can create a function that will download a set of data files from different countries and write them into our hard drive. This can be useful if you do it first in one go, and then you have a data set that you can use to test and debug your program. So this would be a list of all the ISO codes for the countries. This will be the ISO code from a single country. The list is here, and this will will read the data from the remote location. So URL open will give you a file live object that instead of reading from a local file is reading from the server. This is the URL from which it's going to read, and then you use the read function so you get the raw data all in one go from the server. Now we open a file which is called the ISO code that we received .csv, and we open it for writing. We're going to write the data into that file, and this will either create a file if it does not exist, or write all the contents of a file with that name if it exists. And now we're going to write into that text file. Now there is a slight detail here that you have to remember sometimes, but this varies a lot depending on the actual problem that you're trying to solve. But in this case, URL open is returning a byte string, which means that it has all the bytes that it got from the server. And when we write to a text file, we need to encode the text in some encoding, because a byte can only store 256 different values, and we have a lot more of characters. The number of characters that exist in languages in general is a lot more than that. So text files are encoded usually using UTF-8. In Python, the strings are encoded in UTF-8, which most of the characters will occupy 1 byte, but there are some special codes for adding other bytes to get special characters and so forth. So you cannot directly write a byte string into the text file. You need to decode that into a representation for text in one of these standard encodings. And so we're going to decode the content into UTF-8 and write. There are other situations where this problem can arise. For example, if you have a text that is encoded with those Windows code pages for Western Europe or for Eastern Europe, something like that, then you're going to have a problem when you try to read that text, because Python will try to interpret it as UTF-8, and there are some combinations of characters that will be invalid. So in that case, when you open, you have to specify the encoding that corresponds to the text that you're reading. Or if you want to write a text in a different encoding because you need to give it to someone else or something like that, you can also specify the encoding when you're going to open the text for writing. Most of the time you will not have these problems, because even if the text has not the right encoding, maybe there are no special characters there, so these things will not occur. When they do, they will be very dependent on the exact problem that is occurring, or how the text is encoded, what encoding do you need, how you need to process those special characters that cannot be converted, if you want to ignore them or replace them with something and so forth. So I'm not going to go into detail about that, because that is a very specific problem that can occur, especially if you deal with text, but in other cases it rarely occurs. The simplest thing to do in that case is just you look at the error, look it up online, and probably you'll find the solution for that. If it's something that is critical to your work, so you need to know exactly how the conversion is done and how some characters are processed, then I can help you take a look at that and see that in more detail. And maybe you'll even have to look at the documentation and study up a bit on all these text encoding. If your work is mostly with numerical data, you don't need to worry about this, because you're not going to deal with text anyway, so it's not a problem. So what we're doing here is reading all the data from the server, creating a new file, dumping all the data, that text in the file, and closing it. And now we can start with a list of countries, and for each country in the country list, we call the function to save to this. So if we do this once, then we have all our data in our hard drive and don't need to go back to the server every time we run our program. So now we can create a convenience function here that allows us to simplify this decision on whether we want to read from the local hard drive or from the server. This is a very simple example, but there are cases where you may have these branches of options in your code, so there are different ways of processing the data or doing something first, and you want to hide that from the rest of your code to simplify, so that you don't have to be constantly worried about how it was done before. And also, this is an excuse for showing you these default arguments in Python, which is useful for this sort of thing and a lot of other solving a lot of other problems. So basically, default arguments are arguments that you can provide when you call the function or not. If you don't provide it to the function when you call the function, then they already have a value there. And how you do that is when you specify the parameter that will receive that argument, you assign a value to that parameter. So this tells the interpreter that if this function is called only with the ISO code, then this online parameter will be assumed to be true. If someone adds the online parameter and gives a false value there, then it will be used, the value that is provided is the one that's going to be used. But if no value is provided here in the corresponding argument, then it will be true. So this will be a function that by default will try to read the country data from the server. So if online is true, or since it's a default argument there, it's not provided, then we will try to use country temperature, this first function here, to try to get the data from the server. Otherwise, it will read from the local file. So it will use this other function to read from the local file. So you can use the same function to get the temperature data and just add a false argument if you want to read from the local file. And now you don't have to worry about how the rest of the program is built. Now we can get a function to get all the data for all the countries in a single matrix. This is useful if we want to have the years in the first column and then all the other all the values in all the other columns to join everything together. Also, we assume, this is the case for the data, at least the last time I saw it, that each file has data for the same years in the same order, so that we can just easily copy the columns and stack them all side by side. So this function here will receive the list of ISO codes for the countries that we want, and we'll also have this optional argument there with the default value of true. So if this function is called only with the list of code, then it's assumed that we want to get the data from the server. If it has a false there, then it will get the data from the local drive. But here now it's simpler to implement, because we just need to pass on this argument to the next function. So this one is the one that actually does the decision where to get it from, and all the functions that we write later on, we don't worry about the differences between getting from the server or from the hard drive. We just pass on the same argument, and things will work eventually when they reach that decision. So this is another illustration of an important principle in programming, which is solving the problems in small pieces, and once they are solved, they don't raise more problems further on. So we solved this question of getting either from the hard drive or from the server, and now we don't worry about that part. So we're going to read the temperature for the first country, the 0 index here on the list, and this will give us a matrix with two columns, the years and the temperature for the first country. And now we're going to go for all the rest of the countries in the list. So we're going to change this index. This index will be from 1 to the length of the code there, or we could just iterate through starting with the second element of the list. And we're going to read the matrix for each of these countries. Notice that this new matrix will also have 2 columns, the year and the temperature. But now we're going to stack the temperature values into the first matrix. So the first matrix has the years and the temperature of the first country, and now we're going to add the column for the temperatures of the second country, the third, and so forth. And we can do that with concatenate in NumPy, where we send in a tuple of 2 arrays, and we can also specify the axis in which the arrays will be joined. This axis argument appears in many functions in NumPy, and it corresponds to the direction you're going to do the operation here. Axis 0 will be the first dimension, so for example the rows on a matrix. Axis 1 is the second dimension, will be the axis on the matrix. If you have a 3-dimensional or 4-dimensional matrix, you can have more axes. So in this case, we're going to concatenate on the second direction, which is the columns, and so we're going to stack the columns side by side. If we use axis 0 here, we would stack the columns one under the other. And so we need to give, in this first argument, a tuple with the array in a compatible shape. So since we're stacking them side by side, they must have the same number of rows. So we need the first matrix, which has 2 columns with all the years and the data for the first country, and we need the data for the second country as a column also in 2 dimensions, so it can be stacked with the first matrix. And that's why I'm getting from this temperature all the rows and only the second column, but as a column. I need these extra brackets there to retain the same shape. So this seems like lots of confusing details, but this is one of the consequences of having something that is very flexible and very powerful for manipulating data. But you don't need to memorize this in one go. What will probably happen, at least it happens with me, is that you write the code, you test it, and you get an error, and then you remember, okay, I need to change that because it's not matching, or something like that. But you just experiment, and as long as you test it carefully, you'll get it right. And as you get more practice, then this becomes a lot easier to use, and eventually you'll find that it speeds up a lot of these processing operations that you need to do, because it makes it very simple to operate with data. So now we can use this to create an array with all the temperatures and the countries. So this is just to remind you of this problem with slicing. You get if I omitted these square brackets here, I would get a 1-dimensional vector, and then I would not be able to concatenate. Okay. But now we can do this. We have this list of countries. We get the temperature for all the countries. In this case, I did not add the other arguments there. So this online argument, the online parameter will be set to true, and it will get the data from the server. If I already have the data in my hard drive, I can just add a false here, and then it will read the data from the local drive. And now I can do a plot. I create a figure for, I create a plot, in this case, using for the x value the first column, so all the rows and column 0. And then I can do this is very convenient in plotting, that you can put a series, several series of values as a matrix in the y dimension. And the plot will assume that you have the data in columns. So as long as you have your data in columns, you can just give one vector for the x values, and then all the y values for these, and this will plot all your series and changing the colors automatically. This is just to put the legend here, just to illustrate how you can create a legend. You can give a list of strings that is the same, usually the same length as the number of series that you have. If it's not the same length, then some of the names will not appear on the legend. And you can specify things like the number of columns on the legend, where the legend is placed, and so on. There are lots of arguments here. So this is to create this legend here. I'm using the same list as the ISO code, so this will give me the legend in this way. An alternative way is that you can specify every time you plot a series, you can add a label argument that will be the text label that will appear on the legend there. And then the label for the X values, the Y values, you can use LaTeX code for special characters if you want in these text labels and saving the figure. So this we get here the year, the temperature in degrees centigrade, and this is the plot of the data that we have for a different country. So now we can do some things with the data. They are not necessarily the right things to do with the data, but just to illustrate what we can do. We have different temperatures for different countries because they are at different latitudes. But if we want to look at the pattern, how the temperature is changing, we can try to rescale everything to be on the same scale. One simple way of rescaling would be just to divide by the last value, and so this would be 1 for all the countries, and then we compare the rest of the plot. Of course, this is not very accurate because we are in centigrade. Maybe we should do that in Kelvin or something like that, but that's not very relevant. And this is just to show how easy it is to do this rescaling. So what we need to do is to divide all the values of the temperature for each country by the value of the temperature in the last year. And we need to do that in all the metrics. But we don't need to create loops, for loops, and do things like that. We can say that we want to assign to all the rows and all the columns starting from the second one. So we don't want to change the first column because that is the year, not temperatures. So all the temperature columns that start with the second one, we want to put in that place on our table the value that was already there, so all the rows and the columns starting from the second one, divided by the values on the last row and the second column until the last one. So this will be broadcast. This is a vector here. It has all the values for all the temperatures in the last year. And this operation will be broadcast for all the temperature columns on the matrix. Since it starts by comparing the last dimension, this is the dimension here is the number of countries that we have. This is also the number of columns that we have on that table. And so it will broadcast this operation by dividing each temperature by the temperature of the last year for that country. And it will then repeat this for all the rows. So this way we can rescale all the data in a matrix in just this line. So now we can just do the plot again. We can set a limit for the axis. For example, this is the y lim. You can assign a minimum and maximum value to specify a minimum and maximum value for the y-axis. You can do the same for the x-axis too. And this is what we get. Note that everything is scaled to the temperature in 2012. So this is 1, and all the others are relative to that final value. Now we can see that because the temperature varies quite a bit there in the last year, the fit may not be very good before, because everything is dependent on the temperature in 2012. So we can try to do something a bit better. We're going to try to fit all the lines by fitting everything to one reference country and minimizing the error, in this case the quadratic error relative to the reference country. So this means that we're going to start with one reference country, and then for each of the other ones we're going to change the temperature scale there to try to fit it as best as possible with the initial data. Now we can do this in different ways. I'm going to show one where we just rescale the temperature. We could also add or subtract some value, something like that. But the idea is just to show you how you can fit something to the data using these functions in SciPy. So I'm going to use curve fit from SciPy optimize, and this is a function that receives as the first argument some function of your data. So what it will do, it will feed the data into that function and get the result. And then so it will feed the x values into that function and get the result. And then there are some target values, the y values here. It's going to compare the result of that function too, and it will change some parameter that we add here. It can be a vector with several dimensions. In our case, it will just be one value, so that the output of the function best fits the target values that we have. And the best fit is a least squares error, so it's going to minimize the quadratic error between the two. So basically, if you have some function that predicts values from given an input and has some parameters, you can use this to adjust the parameters so that the output is as close as possible to what you want. The function we're going to use this is just a rescale function that multiplies the x values, in this case the temperature of a country, by a scaling factor. So it increases or decreases that temperature. And this is all it does. It receives a list of temperature values and a rescaling parameter, multiplies and outputs those. So since this x here is a NumPy array, we can do this in just one operation because scale is one number. This x is a NumPy array with many numbers, but the product there will be broadcast through all the elements and return an array with all the products. So now we have these rescale temperature functions that receive all the temperatures for the country. So the number of columns that we have will be the number of columns in this temperature, and we can get the number of columns in a matrix by using the shape attributes of the matrix. This shape attribute in a NumPy array is a tuple that has the length of the array in each of the dimensions. So if it's a two-dimensional array, the shape 0, the first element of that tuple, will be the number of rows. The second element on that tuple will be the number of columns. So here we get the number of columns in our matrix. We know that the first column is the temperature, is the year, sorry. So from the second column on are the temperatures from the country. So we're going to start from the third column and fit the third to the first, the third column to the second column. That is the second country to the first country, the third country to the first country, and so on. So we are going to use curve fit. The function that we want to use with the parameters to adjust is that one, the rescaling function. The x values are the temperature for each of the countries, starting from the second one. So we're starting from the third column in the matrix. And the reference country is the first country. So the temperatures of the first country are in the second column of the matrix. And now we're going to compute the factor, the parameter that we need to change there for each country, so that we can adjust the temperatures of that country to our reference country. And we're going to store this into a NumPy array here. So this is the set of factors that we're going to use to multiply the data in our matrix. We can start with a list of ones that have the same number of elements as the number of columns we have in our matrix. So we're going to use this one function. If any of you already use MATLAB, this is the same as the MATLAB function. You put in a tuple with the dimensions, and it returns an array with those dimensions and all filled with 1. In this case, we want a single vector of 1, so we just have one number there, which is the number of columns, and we get a vector of 1 with as many numbers as columns in the original matrix. And now we're going to fill in the factors for all the countries that we're going to rescale. So the first two elements of this factors array will be ones. One corresponding to the years, we don't want to change the year, and the second corresponding to the reference country, which will have the same temperature. All the others will have the scaling factors that we are going to compute for each of the other countries. So in the end, we can just multiply our original table with this array of factors. It will leave the years unchanged and the temperature for the reference country too, because for those the factors are 1. But for all the other columns, it will change the scale of the temperature depending on the factor that is specified. So this way we can now load all the temperatures. Note here that I'm going to use as this argument false, so I don't want to read from the server. I already have the files on the drive, so I read from the drive. I'm going to rescale everything and plot on a chart. This is the same basic code for doing the plot, and now we have this result. Note that this was what we did, what we got when we rescaled to 2012. This is what we get when we do the rescaling by rescaling each country so as to minimize the quadratic error to the reference country. Okay. We get something that is a bit closer overall. Now it no longer matches in 2012 because it may need to rescale a bit differently because of the other part. Okay. So these are different ways where you can, different elements of these libraries that you can use to fit your data, to rescale your data, or do some pre-processing. Now let's average everything. So we get, we can do this function to do this averaging. It rescales the temperature. It calls the other function to do the rescaling. Then it creates a new matrix which has two columns, so it's all filled with zeros. It has the same number of rows as the original data table, so we're going to go to shape that tuple with the length and get the first element, which is the number of rows, and we want two columns. This will be a table for the average temperature of all the countries after rescaling. And we're going to put in the first column of this table just a copy of the first column of the original table, because this is just the years and we just want to copy the years. For the second column of the average table, we're going to compute the averages for our original table for all the columns except the years. We don't want to put in the years in the average, we just want the temperature. And we're going to specify that we want the average to be computed on the first axis, that is, going in the direction of the columns. This means that we're going to have an array with the same number of elements as the number of rows that we have, and for each element of that array we will have the average of that row computed over all the columns in that row. Okay? And this only for the part of the table that does not include the year. So this way you can compute the averages for all the years, for all the countries in one go, and just put it on the second column of our average matrix. And now we can do the same thing in plot, and so we have here, this is the average of these values here, these ones after rescaling. We are averaging for all the countries. So you see these are very common operations that you usually have to do with data, computing average over rows, over columns, and so forth. And it's easy to do with these functions where you can specify both the data and the direction where you want the average. If I were to say here x is equal 0, then it will give me the average of each column and a vector with the same number of elements as the columns I was considering. Okay? Now we have too much variation here between the years. We can smooth things here with a moving average, and that is, we can use a window of some size, and then we consider a slice of the values, and we average that, and then we move the slice forward to get the average over that window along the sequence. So in the end, we're going to have as many elements as the length of the original sequence, minus the size of the window, plus 1, that is the number of elements that we have in the end. The larger the window that we use, the fewer elements we'll have in the end. So we can write this function, moving average. We have the values, the size of the window. We create this moving average array filled with zeros and with the correct length, so the same number of values we started with minus the number of the size of the window plus 1. This will be the final array. And now we can loop through the indices for these slices that we want to compute. from our original data, and we're going to start with the same index as the window and go all the way to the end of our values here. And now we're going to compute the moving average by subtracting the window from the index. So basically we have the slice point starting, in this case the first one starts at 0, and since the window is 3, it ends at 3. So this is what we're doing here. We're going to put there on the first element of this array when the index starts equal to window, so this will be 0. We're going to add the values of this slice from the index minus window to the index. Since the index starts at 3, we'll start here at this point, at slice 3, then go to 4 and so forth, and the first, the starting point of the slice will also be increased. So we can do this, and we put in that array the sum of all these values divided by the size of the window. This will be the average, or we can just compute the mean or something like that. So this gives us an array with a moving average. We can do this a lot faster if we use the cumulative sum of the values. So this is just to show you that sometimes you can implement something in a way that is less intuitive but can be a lot more efficient. Most of the time you will not need to worry about this, because usually you'll have to process your data once, and if it takes a bit longer, then it's not a problem. But if you have something that starts taking a lot of time, you can look at the code and try to see how to optimize it. And in this case, the big difference is that if you do a loop in Python, it's a lot slower than if you just use the capacities or the functionalities of the NumPy array to do these operations in one go. So what we can do here is we obtain the sum, the cumulative sum of all the values using this sum function. So what this does is it's going to keep adding the values. This is the original, for example, and this is the cumulative sum here. And then we can compute a moving average by computing the difference between the elements that are at the edges of the window. So if we subtract, say, from 21, we subtract 10, we get the sum of the elements between these two, because this is the cumulative sum so far, and we are subtracting all those that came before. And we can do that easily by doing something like this. The cumulative sum from the window to the end will be what was already there. So from the window is the first point of this slice up to the end, subtracted by the same thing but starting from the beginning. So we start from the beginning and we end at minus window from the end. So we have two slices of that cumulative sum that are offset by the size of the window, and so when we broadcast this difference operation, we are subtracting one from the other all the way to the end. And now we can just get the values here. So we start from window -1 until the end. We ignore the first here, and we divide that by the size of the window. We get the same moving average. So this is less intuitive, this implementation, but the example here is only to show you that you can start with something that is easy to implement because you understand how it works. If it's too slow for what you need, then you can look at ways of implementing it with more efficiency. But usually, if you don't need that, it's not useful to make the code more confusing just to get a few extra seconds out of your running time. So in general, you won't have to worry about this unless you really have to process a lot of data and it's taking hours or something like that, and you want to make it faster. So now we have a window of 10 years here. We're going to compute the moving average. So doing everything from the beginning, we get the temperatures. In this case, false means we're going to read from the hard drive. We rescale everything. Then we create a copy of the average, average temperature here in that window that we want to compute the moving average for. So this is basically so that we get the original years that we can use for plotting, and then we're going to draw the moving average there, the year, and so forth. So this would be the smoother version of this chart here. This would be for every year, and now we have here the moving average for overall these years with a window of 10 years. Another thing that we can do is, instead of a moving average, we can try to fit a curve to our data. We have data for all these years. It's changing a lot, but we can smooth that with, for example, a second-degree polynomial. This is something that we can do easily with NumPy. We have this polyfit function here. We give that to the function the x value and the y value for the polynomial and the degree, and it will return the coefficients for the polynomial that best fit that data by minimizing the quadratic difference. Now, there is one slight trick here, is that we are dealing with x values that go from 1900 to 2012, and so if you use that as x on a polynomial, especially if the degree is higher, you can get numerical problems because you then start having very large numbers as you raise that to the power of something. So one trick when you're trying to fit these parametrical curves is to rescale your data or change the scale of your data so as to minimize these problems. And that is what I did here. I created this relative year array, which is simply subtracting the first year for everything. So I'm not measuring the years from 1900 and so on. I'm measuring the years from 1900. So I only go from 0 to 112. You can also do this and rescale everything, for example, to between 0 and 1 or something like that. But this is sufficient for solving the problem here. And now I'm going to do the polynomial fit to the relative years. So I'm not dealing with thousands, I'm dealing only with more reasonable values. Now I compute the values for the polynomial. So in this case, there is also a function called polyval that you can use to evaluate the polynomial. But here I'm just illustrating these kind of operations also with the numerical arrays. The result of the fit is using the relative years. I'm going to use each year squared. So this is a NumPy array. I can square this for square each element, and then multiply by the first coefficient of the polynomial, and this is also broadcast by NumPy. Then I do the same thing with the second coefficient and the relative years, and add the constant there. So this is just the expression for the second degree polynomial. You don't need to do it like that because you have a polyval function that evaluates the polynomial, but this is just to illustrate again what you can do with the NumPy array. And now we're going to plot the data, the original data, as dots there. Note that I'm going to use the actual years as the x values now. I only use the relative years to compute for the polynomial, but when I plot on the chart, I use the years in the normal scale. And then I'm going to also put in the fit, the result of the fit. So this is the result here. I have the rescaled and data, but not with the moving average. So this is the averages for the countries for the different years. And then I fit this polynomial curve to that data, the one that minimizes the quadratic error and gets the smooth version of that data there. So this, none of this is actually how you should deal with temperature data. I have no idea what you should do, but you have different examples here of rescaling the data, extracting the data that you want, getting data from online servers, and then fitting some model to the data. So it can be a polynomial curve, it can be other things. I'm going to show now in this next example a more sophisticated model. So this one is a bit trickier, because those of you who don't come from biochemistry, this is basically an experiment that you can use to determine how the substrate concentration in some biochemical reaction affects the velocity of the enzymatic reaction. So you have an enzyme that catalyzes the reaction, and depending on how concentrated the substrate is, what the enzyme works with, you can change the speed of at the beginning of the reaction. So you can measure those velocities for different concentrations of the substrate, and you can get a plot that looks like this. So as you increase the concentration of the substrate, the initial velocity of the reaction increases. But at some point it starts to saturate, and it no longer has any effect. Increasing the concentration of the substrate cannot speed up the reaction because the enzyme is already being used at the maximum rate it can be used. So this is the curve here. In this case, it follows this Michaelis-Menten kinetics, but this is the formula for this shape, the shape of this curve. We have this maximum velocity. This is what the curve will tend towards as we increase the concentration of the substrate. And we have this Km value, which corresponds to the concentration of the substrate that gives us half the maximum velocity. So this is the midpoint here on the curve. But this is just to show you how we can fit also the model when we have some arbitrary expression for the relation between the variables. So this is the relation between the initial velocity that we measure and the substrate concentration controlled by those two parameters. The maximum velocity, which will be where the reaction will saturate, the speed will no longer increase, and this Km value, which gives us the midpoint to that maximum velocity. So we have this data, we have a file with the concentration of the substrate in the first row and the measured initial velocity on the second row here. And before we had computers, we could solve this by computing the logarithm. This would give a line on the logarithmic scale, and then we could do a linear regression there to get these parameters. The problem with that is that then when we do a linear regression, we are minimizing the quadratic error, but in that case we would be minimizing the quadratic error to the logarithm and not the actual value. So we need to do that to linearize the expression, but now the error is something strange because it's the error to the logarithmic values and not the actual values that we have. With computers, we don't need to do that. We can just use a numerical optimization to actually adjust the parameters to the actual data. So we need to find a reasonable cost function. The quadratic error is a reasonable cost function, and adjust the parameters to minimize that error. So let's write our cost function, what we want to minimize. We get here an array, a vector, well, it can be a list or a tuple, it doesn't matter, with the parameters that we want, that we have for this equation. So this would be the Vmax and the Km parameters here. And we have the substrate concentration and the measured initial velocity. These are the data that we are going to compare our model to. So now we're going to compute the prediction, which is for each value of the substrate concentration, we apply the expression there to get the predicted initial velocity. And so the first parameter is the Vmax here, the second parameter is the Km, and we just write this expression. So this is the Vmax multiplied by the substrate concentration divided by Km plus the substrate concentration. Note that this F can be an array of values. We can use all the data values that we have here in a NumPy array, because these operations will now be broadcast over all the array, and we get a vector, an array with all the predicted values. So these predictions will be the Vmax, the initial velocity predictions for all the concentrations of substrate. And now we can compute the cost, which is the quadratic error between the predictions and the observed values of the initial velocity. So this is simply V minus the prediction squared. This gives us, this squares all these differences, so all these operations are broadcast over the array. Since these arrays must have the same length, we have the same data points for velocity and substrate concentration, and then we add everything here. So this is the total quadratic error for one specific pair of values for Km and Vmax. And now we can use this in the minimize function. So we go again to SciPy optimize, we import this minimize function. And what this minimize function does is you need to supply a function to minimize. It's going to try to find the minimum of that function. It's something similar if you use solver in Excel or something like that, where you try to adjust parameters to minimize a result. So this is the function you're going to minimize. This is a list of initial guesses for your parameters, so this will be the starting point. And the dimension of this list tells the minimize function how many variables you're trying to adjust, so how many dimensions you have in your optimization problem. Then you have this arg parameter here. You can supply as an argument a tuple of additional arguments that the minimize function will pass on to your cost function. Note that the minimize function doesn't care what you put there. This is just additional data that your cost function may need, and in our case it's the substrate concentration and the initial velocity. And then you can also specify constraints for the optimization. In our case, none of these values make sense if they are below 0, so they cannot be negative. So we specify for each of the directions, for each of the variables we're trying to adjust, these bounds that are 0 at the lower bound and none at the upper bound. This means they don't have an upper limit, but they cannot be negative. So we specify these for our variables. You have other options here for the kind of algorithm that's used for minimization and derivatives and things like that. There are many more sophisticated ways of doing minimization with SciPy, but in this case this is a simple problem and it's easy to find the answer. So when you compute minimize here, you get a result object that includes things like the number of iterations, the error, and so forth. And the way this works is that minimize function will start by measuring the error if we use these parameters, so one for Vmax and one for Km, and then we will change the values of the parameters, see where the error is reducing, is lowering, and it will keep changing that until it converges to some value. So it's going to do a numerical minimization of that function. This result object has this x attribute which has an array with the final value. It has the same dimension as what is specified here, but has the final values of those variables that you are adjusting. So we can unpack that into Vmax and Km and return this. So this is how we can now model the data and plot it. We're going to use this common trick, which is to create, when we want to draw a curve on some chart, on some plot, we can create a set of x values that have lots of points, because then the plot will always join points together with straight lines, but if we have a large number of points, it will appear to be a curve. So we're going to create 200 points between 0 and the maximum of our substrate concentration multiplied by 1.1. This will just make the curve go a bit beyond the last data point. And we will create 200 points in that array. So what this link space does, it's going to start at 0. The last value will be what we specify here as the upper limit, and the array will have 200 points uniformly distributed in that range. So this is good for creating an axis for plotting something. We're going to we can use this for any Vmax and Km. So we're going to compute the epsilon, the y values for the Vmax and Km for these x values here. So to draw the line, and we're going to create a figure for plotting. We're going to plot this line in red, and we're going to also plot the data that we receive as blue crosses in that chart. So we get something like this. This is, if we put into that function, this is just a function for drawing any of those curves. Note that the Vmax and Km are received there as arguments, and we can now do this. So this, to adjust the model, we load the data from our file. This was the file that we have. We have the first row of the data is the Vmax, the substrate concentration. The second row is the Vmax here. We can give our data to the just model function that calls the minimize of SciPy. So it's going to get the substrate concentration from the first row, the initial velocity from the second, and return the adjusted parameters. And then we plot the model with the adjusted parameters. So after we build these functions, we can just load the data and plot the result. And this is the original data, and this is the curve that we adjusted, and here are the two parameters that we found. What we can do, this is something that you can also do with other tools, or even without computers you could do by linearization and so on. So just in this case, finding the parameters themselves is not something that is very different, although if you implement this, it becomes a lot more practical if you have to do it many times. But there is something that you can do with programming and the computer that would be very hard to do by hand, which is this sort of methods by which you can estimate error margins by resampling, by repeating the experiment and recomputing those statistics. So bootstrapping is a way of doing that. It's a generic method for resampling. So let's suppose that we wanted to get an idea of the confidence interval for our values, the values that we estimate. One way we could do this would be to repeat the experiment. If we repeat the experiment 100 times, then we compute the Vmax and the Km for each repetition of the experiment, and then we get an idea of how they vary over different experiments. Of course, repeating the experiment 100 times would not be very practical, but we can pretend we repeated the experiment by resampling from the data that we have. And the idea here in abstract is that the points that we are getting here when we do the experiment are a random sample of a conceptual universe of possible results from our experiment. We can try to obtain a new sample from that possible universe by resampling the data we already have. So if you have a set of data that you obtain, you can resample from that data, and the distribution of values is similar to what you had in the universe. So this is the bootstrapping method. You resample with reposition from your data. This means that you can get repeated values from the sample you already had, but some of the values will not be present because you are sampling from your data and obtaining the same number of points at the end, the same size for the new sample. So you can do that in general, bootstrapping, and do this resample and obtain a set of samples with a similar distribution as that of the original universe from which you got your original data sample. In this case, it's a bit more complicated because although the values that we measure have some random error, and we can consider those to be a sample of the possible values that we could measure in this experiment, the concentrations for the substrate are not measured. They are decided. We decide to do the experiment at this point. So we can do a variant of bootstrapping here, which is residual bootstrapping. Let's suppose that we have this best curve that we found, and each of our data points has some residual error relative to the curve. It may be above or below the curve. And this is due to some random effect. So any point could be above or below depending on how the experiment went. So what we can do is we can assume that this is the result of random sampling from a universe of possible errors that may occur to our data. And now we can resample using this set of errors that we have here and generate a new data set by randomizing those errors. So we resample from those errors, we add them, the residuals, to the best curve that we have, and we have something that could be the data from a new experiment using the same distribution of residuals that we already measured in our original data. And now for each of these new samples, we can compute a new curve for here, And from this curve, we'll get a Vmax and a Km value, and so we can get an idea of what is the overall result, the average, the standard deviation, and so on. We can get statistics for our parameters by iterating through all these samples. So what we can do here in this way, we are going to do n replicas, for example, 500 replicas. To do that, we have the best curve, the Vmax and Km that we obtained for our original data, and we're going to use that to compute the residuals. So the residuals are the differences between the actual measured maximal velocity and the predicted one according to our best model. And now what we're going to do for each replica is we're going to sample these residuals at random with repetition. So they can be repeated, they are never, or they are very rarely occur that we have exactly the same set of residuals because they have lots of different combinations. And we're going to do that by creating, using this random module in NumPy, and get a NumPy array with a random set of integers that go from 0 to the number of columns that we have in our data. And we have as many of those as the number of columns that we have. So basically, for each data point that we have, we are throwing one die and see which residual we're going to assign to that point. This can have repetitions, and it's at random, so each time we create a new replica, we have different residuals here. And now we're going to create a new data set by using the best curve and adding these random residuals there. So basically, we are starting from this blue curve here. We are randomizing those red errors, those red residual errors, and using that to create new data sets. Now we're going to minimize and we're going to append the result, which is the Vmax and Km values into this list. So now we have a list with the Vmax and Km for the first replica, the second, the third, and so forth. We convert that into a matrix, a NumPy matrix. So basically what we get from here is a matrix with 500 rows, because we use 500 replicas, that has in the first column all the results for Vmax, and the second column all the results for Km, assuming that the errors we have relative to the best model are a random sample of the possible errors that we could have in our experiment. And now we can compute the average and the standard deviation. So in this case, I'm going to compute the mean and the standard deviation using an axis of 0. I'm going along the row and computing for each column. So this is for Vmax and Km, and the standard deviation here. And I can also represent the results. So this is using semi-transparent curves. I'm going to plot all of these curves, and I get an idea of how they are spread out over the best model that I have. And also I can plot the histograms for the values I've got. So this is the distribution for Km. It goes from around 2 to 6, but mostly here around 3.5. And this is the distribution for Vmax over all these data. So if I had more, if the data was poorer than this, so if the residuals were larger, then I would have a greater range of values in the end. If the data is very good, then things will be narrower. And this is an easy way to implement in Python for you to get an estimate of the confidence interval for your parameters by resampling your data and computing these statistics. Okay? So this would be very hard to do with a spreadsheet, for example, because you need 500 replicas, but it's only a few lines of code, and you just expand the program that you already have and can compute these things easily. So to sum up this part, note that we keep reusing these same basic elements, loops and functions and so on. So I hope you recovered from last week, but now we can go back to that repeatedly as much as you want. But now we are looking at some specific tool sets for more practical problems of actually handling data and processing data. So in this morning we looked at NumPy and SciPy, which is basically the basic tool set that you need if you're working with numerical data. You need to process data and fit models and then plot everything. So this will be the basic libraries that you're probably going to need. The details here are not very important for you to memorize now, just to get an idea that things can be done in this way. Then you can go back to the slides, and as you practice, things will start to become more automated. In any case, you have lots of examples and documentations also online, aside from the examples I gave you. So if you have specific problems, it's easy to just go online and look up similar solutions.